All right, everybody, welcome back. This is actually a continuation of Chapter 4. We have it labeled here as Chapter 4 and 3/5, but you might want to call it Chapter 4.5 or whatever you want to call it. But it's really just a continuation of vectors. But we're looking at a specific kind of vector addition, particularly in the realm of relative motion and kinematics, which you've had, but and by kinematics we mean velocity, acceleration, displacement, that kind of thing, but in two directions or two dimensions. So you would need to be able to add vectors to do that. So this is our chapter, you might say 4.5 notes right here. And the big idea, at least in this first part of relative motion, is the concept of a frame of reference. It's basically a coordinate system, or it's just a means by which you can tell if something is moving or not by comparing it to something else. For example, you're probably sitting here on a chair watching this. Ask yourself, are you moving? Okay. Well, probably not with respect to the chair or to the room. You seem pretty stationary, but you are moving. You're moving, the Earth is turning, so therefore you're moving with respect to space, or you're moving with respect to the other planets or the sun. So it's just by which you measure your position or your velocity or your acceleration or anything. So you're comparing one object's motion with respect to another. Okay, so if two things are moving at the same point, for example, like two cars, so we've got a car right here on the highway and a car on the highway right here, and they're both moving, so they're on like a two-lane highway. They're both moving at the same speed in the same direction. They're basically the same frame of reference. Why? Because one person looks over at the other person looks back at him or her, and they appear not to be moving. So it's like, okay, well, we have basically the same point of view. Everything, the trees and houses seem to be zipping by them both at the same speed. So you could say they're at the same frame of reference. But most frames of reference that we're going to talk about are things that are different with respect to each other. Like, say there was only one car moving. Okay, it's moving in this direction right here. I should have made that a different color. That's all right. And then everything else is moving past it. All right, we're going to compare this car's motion with respect to everything else moving past it: the houses, the trees, the road, and so on and so forth. So a frame of reference is really how something is moving with respect to something else. So this brings up the notation for relative velocity. So let's say we've got a car, like I said before, and here's our car. It's moving in that direction right there, and it's moving over the road. Let's change to black right here. All right. So if the road, and we'll put some dots on the road to indicate the road is stationary right there. The car is moving over the road at some speed. I don't know. Velocity equals 30 meters per second. All right. Well, if another car was right next to it, it wouldn't be appearing to move at 30 meters per second. But if you were standing next to the road, if you were the road itself, the car would be appearing to move over you at 30 meters per second in a certain direction. So that's where we have this notation right here. So we would say, really, the object that is moving, we call frame of reference A. So in this case, it would be the car. All right. That's the car. And the object that it is moving with respect to or relative to would be the road right here. So that would be the road. Okay, so we would call that, so we could actually label this velocity right here. The velocity of the car with respect to the road is 30 meters per second, and we should give it a direction that looks like due east, right, or at 0 degrees east, so 0 degrees north of east. Okay, so it's always the one object that is moving with respect to the second object right there. Okay, so these this notation, these little placeholders of object A moving with respect to object B, these are going to be very important because the next slide is going to be an equation where these objects are going to make all the difference right there. All right, so you could say that a car moving over the road, so here's our car, is moving over the road. Generally speaking, the road is stationary, and the car is moving over it. But it's just like saying, here's our car, okay, and it's just like saying the road is moving underneath the car, but in the opposite direction. All right, now, generally, we think of the car as moving over the road, but if these are the only two frames of reference, would you know whether the car is moving over the road or if the road is moving under the car? And the answer is you wouldn't. So we can really say that if we want to change around this notation right here, we could say, all right, the velocity of the car with respect to the road is 30 meters per second at 0 degrees east, 0 degrees north of east. Or you could say it like this. The velocity of the road with respect to the car is 30 meters per second, but it's in the opposite direction, right? It's at 0 degrees west, or 0 degrees north of west. All right, this is going to make all the difference because having these subscripts in the right order is going to be very important to us. So even though we have it's still 30 meters per second, this direction right here tells us that if we change the order of the subscripts, it changes the direction of the vector. So this right here, this boxed equation, is going to be a really important equation for this whole section. Let's say we have two frames of reference now, or you might say three parties that are observing each other move. We can say, and this is the general equation right here, that the velocity of object 1 to object 2, okay, and the velocity of object 2 with respect to object 3, whatever that is equal to the velocity of object 1 to object 3. You might think of it like this. Okay, you're a person that is moving, you're walking that way on a platform. Okay, so or on, we'll say the, well, I'll just say it right now. It's one of those rolling walkway things that you see in airports. Okay, and you're walking over that at 2 meters per second. Okay, so the velocity of the person to the what are we going to call it? The conveyor belt. Okay, to the conveyor belt equals 2 meters per second. But it's also true that those things are moving, and the reason they move is so that we can move over them, move over the ground more rapidly and get down to the end of the airport terminal. So this thing, in fact, I'll kind of recolor this thing red right here. This thing is also moving, so it also has a velocity, the velocity of the conveyor belt with respect to the what? Well, it's moving over the ground. Equals, we'll say, 3 meters per second. All right, so how fast are you moving over the ground? Well, the velocity of the person with respect to the ground is this vector here plus this vector right here. So you're really moving over the ground at 5 meters per second. That's what this equation here means. All right, the velocity of 1 with respect to object 2 plus the velocity of object 2 with respect to object 3 equals velocity 1 with respect to object 3. That's really what we did right here. I'm going to write this all in black again so we can say the velocity of the person to the conveyor belt plus the velocity of the conveyor belt to the ground equals the velocity of the person with respect to the ground. All those are vectors right there. This is going to be our working equation for doing relative motion, because as you move over an object that is itself moving over a third object, you want to be able to find what your motion is with respect to that third object right there. So we're going to get into some examples in the next subsequent videos, which is going to show you how we actually apply this principle right here. We'll see you then.